environment here nearby, and it's an amazing place to do science. So it's a real pleasure to be here to accept this award and give this talk. So I'm going to talk today about how I see using AI to accelerate scientific discovery itself, and I'll also give just a quick preview of how we got to the point we are now with working on things like AlphaFold, and then I'm going to talk a little bit about how I see things going into the future using AI to accelerate science. So we founded DeepMind back in 2010. It's almost like another age now, it feels, in terms of AI time. But it was only, of course, 13 years ago. And back in 2010, nobody was using, no one was really thinking about working in AI, certainly in industry. And it's kind of amazing to see what's happened just in a few years, going from 2010, where it's very difficult to raise any money to work on AI in industry, to now with billions of dollars going into AI projects. And it's been an incredible process to watch and be part of. And we founded DeepMind in 2010 because we thought a lot of progress could be made if we brought together hardware advancements, algorithm advancements, and some knowledge about how the brain worked, and get some inspiration from the brain for certain types of algorithms and systems, and bring that all together with amazing engineering. And we felt back in 2010 that some very fast progress could be made. The kind of progress that we've seen, although even that I think has been surprising to even those of us in the industry. So we tried to kind of form this Apollo program-like effort at DeepMind to bring together multidisciplinary groups of amazing researchers and engineers to make the most progress we could as fast as possible. Our mission statement was to try and solve intelligence and then use it to advance science and benefit humanity. By solving intelligence, what we meant was trying to understand the nature of intelligence and then recreate that in an artificial construct. That, I think, is the science of AI. So we've started off, our first big result was with classic Atari games from the 1970s, and our first system called DQN, Atari DQN, was our first sort of successful big system, really. Back in around 2013, we got this working. And what it was able to do is demonstrated, I think, the power of learning systems. It was the first really big system that was an end-to-end learned system. So the innovation here was that we didn't give the rules of the game or the criteria of how to get points or anything to the system. All we gave the system was the raw pixels on the screen, and it had to figure out everything else from first principles. And being told the goal was to maximize the score, and that's it. Had to figure out the controls and how to get points and so on. And so at the time, this was pretty astounding because no one had ever sort of done something at this kind of scale. 100 by 200 pixels, so the input was 20,000 pixels, and that was pretty huge for any kind of neural net or learning system. This DQN system went on to kind of learn to play any Atari game to better than the best humans can play and get them to sort of maximize the score. So for us, this was a watershed moment. I think quite a watershed moment in the field in terms of what these learning systems might be able to do if we train them in the right way. So then, as Martin mentioned, probably one of our biggest results, the biggest one we had in gaming, was AlphaGo, which was our system in around 2015, 2016 that we built to learn how to play Go through a self-learning process that I'll describe, and kind of famously managed to beat the world champion at Go, the legendary Lee Sedol, the South Korean grandmaster. And why is Go so much tougher than chess and other games to play? Well, partly it's the complexity of Go. Humans have played Go for thousands of years now. It was invented 2,000-3,000 years ago, still as popular as ever today, over 40 million active players. And one measure of the complexity of it is that there are around 10 to the power 170 possible board positions in Go, which is far more than there are atoms in the observable universe. So there's no way to kind of brute force search through this incredibly complex combinatorial space in order to figure out what the right moves are. And the other extra thing that's hard about Go is, and you'll see a Go board on the right there, is that it's quite an esoteric aesthetic game. It's one of the things that makes it beautiful. And it's very difficult to write heuristics or rules down about how to evaluate how a machine might evaluate a position and evaluate who's winning, so-called evaluation function, which is critical to machines playing these types of games. And in chess, it's because it's a material game, it's a lot easier, and a calculation game, it's a lot easier to actually specify what these heuristics are. But in Go, that's kind of impossible. So people have spent 20 years prior to AlphaGo trying to handcraft these heuristic systems to kind of describe the aspects of a Go position. And one of the issues is that because Go is such an intuitive game, even the top human players, grandmasters like Lee Sedol, they don't really think about it in terms of calculations and rules. It's much more about feeling and intuition, which are traditionally two things that you would say are difficult for computers to do. So AlphaGo went on to win the match 4-1 in Seoul in 2016. Pretty famous match. It became over 200 million people watched the match around the world. And there's a fantastic YouTube documentary on it, award-winning documentary on it if you're interested to see how that played out. But the interesting thing was not only the fact that it won the match, of course, but it was also how it won that was pretty surprising. And actually, AlphaGo created new strategies in Go that had never been seen before, even though we've played this game for thousands of years. And the most famous one of that was Move 37 in Game 2 of the 5-game match, which astounded the Go world and is still being sort of studied today. And Move 37 is that black stone circled by the red there on the board. And this early in the game, it's sort of unthinkable to play that near to the center of the board. It's sort of not considered to be a good strategy at all. And in fact, when the professional commentators were commentating live on this game, they thought there was an error in the computer system in order for it to play there. So it was such a surprising move. And it's interesting actually just to touch on, and maybe we can touch on this in the Q&A, is what does this mean about creativity and intuition, these sorts of aspects that we think are very cognitive. And I think when I reflect back on this, I would say that there are at least 3 levels of creativity, and perhaps AlphaGo and systems like that, the current systems we have, exhibit the first 2. So if we think about interpolation, that's, if you imagine, you ask us one of these generative systems to imagine, show a picture of a cat, maybe it would have seen millions of pictures of cats before, and then it does some kind of interpolation or averaging of all the cats that it's seen, and then it produces a sort of prototypical cat and outputs that as an image. So, that's an original cat. It doesn't exist in the training set, but it's a simple sort of matter, relatively simple matter of kind of averaging across the exemplars that it's seen. The second type of creativity at the high level is extrapolation, where you sort of sample the distribution. And so in AlphaGo's case, maybe you look at all the human games that have been played online, and you start building up patterns of what are reasonable things to do in Go, reasonable positions. But actually, you then not just simply average what you've seen, but you actually extrapolate these motifs into new parts of the distribution that perhaps they're not in the training set, beyond the training set. And I think this is what Move 37 is, and AlphaGo has clearly, and systems like this have clearly demonstrated. And I think that's very exciting if you think about the potential for that in science, to extrapolate beyond, make models of the current distribution we can see, and then extrapolate to come to new conclusions and new ideas that are beyond the boundaries of what we have data for. And then finally, and I think today's systems don't do this, maybe we can call it invention or out-of-the-box thinking, which I think is an even higher level of maybe abstract creativity that, of course, we as humans do effortlessly, but so far I would say machines don't do. And I think the easiest way I can give you an example of that is, of course, AlphaGo was able to make these amazing creative strategies in Go, but it couldn't invent Go, right, or invent chess. That to me would be a new level of invention. And I don't think that's impossible. I think it's just partly actually maybe the limitations of the current systems, but also the limitations of the way we're able to describe the goals to these systems. So I think if you were to get a human game designer, like I think the sorts of things I used to do to try and come up with Go from scratch, you might say something like, come up with a board game that is beautiful aesthetically, that takes 5 minutes to learn the rules. There's only a couple of rules for Go, but takes maybe multiple lifetimes to master, and you complete a game in maybe 6 hours, so within a human life afternoon, so to be convenient. So maybe you would specify these kinds of goals, and then Go would be an answer to satisfy those goals. But you can see that would be very high level specification if one was to do that, which so far our systems wouldn't, I don't think, be able to cope with that. So just to explain a little bit about how AlphaGo works, and I'm actually combining several pieces of work here together when I describe this. This is a sort of simplified description of how all of these types of systems work. This includes AlphaGo and its successor programs, AlphaGo Zero and AlphaZero. And AlphaZero actually is a kind of general games playing system that can play any two-player board game, a perfect information game, better than world champion level. And so the process is actually quite simple to describe. So you start off with a neural network, initialized neural network that basically plays randomly. And you can think of that as version 1 of the system. And it plays around 100,000 games of whatever board game it's playing. That creates a data set of these 100,000 games and all the positions in those games. And then you train a second version of the neural network on that data set. And what you're trying to do here, the neural network's got two jobs. It's got to predict the probability of who will win from that particular position, and how likely they are to win, whether it's which of the two sides will win, and also what are the more probable moves that might be tried in a certain position. So that's the sort of two prediction jobs of the neural network. Then when you train version 2 on this version 1 data, you have a little 100-game tournament, and you match off version 2 against its predecessor. And you have this 100-match game, and then if it wins a significant amount of time, we set the threshold to be 55% win rate, then you replace the current system with the new one. So you replace version 1 with version 2. And then you do this whole cycle again. You play another 100,000 games, but this time version 2 playing against itself. You generate a new data set, slightly higher quality because version 2 is slightly better than version 1, and then you train the version 3, and that matches off against version 2. Now, if version 3 turns out not to be better than version 2, statistically better, then you continue to generate another 100,000 samples with the current version 2. So you end up creating 200,000 games then for the new version 3 to be trained. And eventually, the new version will beat the old version. And if you do this system in terms of Go 17 times, different games require different amounts of cycles, you go from playing randomly to better than any entity on the planet has ever played Go. And it's quite a thing to watch live, especially in something like chess, which I know well. You start the process off in the morning at breakfast, around coffee time at 11 a.m., you can still beat the system, and then by lunchtime, it's better than world champion. It's actually quite amazing to actually watch that live as you're sort of going through your morning. So it's quite a thing. And it's very visceral if you play chess or play one of these games to see that live in front of you, that whole process. So what's going on here then? Well, effectively, if one thinks of a Go tree as the tree of all possibilities, and you imagine each node in this tree is a Go position, so you're currently in this, the current position is the top of the tree, and you've got this enormous, set of possibilities from each position, the 10 to the 170 possible positions, and you've got to find this sort of classic needle in a haystack. How do we decide what the optimal strategy is, the optimal move to play from this kind of position in a very finite amount of time, maybe 1 minute of thinking time? So clearly it's not tractable to do this in any kind of vaguely, any kind of brute force way or exhaustive way. So what we're basically doing is guiding the search with the model. So the model is coming up with most probable moves and the kind of most interesting moves to look at, and therefore guiding the tree search to be very efficient in the budget that it uses. The sort of Monte Carlo tree search, maybe it can only search around 10,000 moves per decision, and it's got to apply that very limited search budget to most appropriately to the entire search tree. And then when it runs out of time, of course, then it outputs the best plan, the best tree that it's the best sort of path that it's found up to that point. So we've been pretty lucky, and using games, and we started with games. I mean, partly obviously my background in games, and I try to utilize every single strand of the things I've experienced in my career to bring them together to always make use of them. And I always had in mind, even though as Martin was describing all these different things I did earlier in my career, from probably around 14, 15 years old, I had already decided that AI was going to be my career, and this is what I wanted to do with my life. And then all the other things I picked to do, from the PhDs to writing AI for computer games, was sort of in preparation, if you like, for doing something like DeepMind. And then we made use of all this games knowledge, and we have quite a lot of amazing games engineers, ex-games engineers at DeepMind who work on these simulations and work on these programs. We worked on games because we thought it would be the fastest way to make efficient progress with testing out algorithmic ideas. And that turned out to be the case, and we were fortunate to make a whole bunch of big breakthroughs. I just talked about DQN and AlphaGo and AlphaZero, and then we culminated in this program called AlphaStar, which beat the grandmasters in the most complex computer game, strategy game called StarCraft 2, which has all sorts of other challenges from board games, like partially observable environment, and it needs long-term planning and other big challenges. So with that, games has been phenomenal for making progress over almost a decade worth of work to get the algorithms to a point where they were sophisticated enough to be applied to challenging real-world problems. And of course, that's problems, commercial problems and industrial problems, and pretty much every system that you use now at Google has a piece of DeepMind technology in it, from the way the massive data centers are cooled to the voice on any of the devices that you speak to. The Google device you speak to, I use WaveNet, which is the world's best text-to-speech, most realistic text-to-speech system. A piece of DeepMind technology is sort of in almost every service. But for me, my personal passion, as Martin was saying, is to eventually, the plan was to use AI as this incredible tool, almost like the ultimate tool for helping accelerate scientific discovery. And I think in the last few years, maybe 2, 3, 4 years, I think that's become possible, and I think it's a really exciting time now in AI to do this, to bring over all of these amazing ideas that were developed in areas like games and other theoretical domains, and bring that to real-world important problems. So for me, I always had my eye on, and I learned about the protein folding problem, and I'll describe that very briefly for those of you who don't know what it is. In my undergraduate in the 90s at Cambridge, I had quite a lot of biologist friends there, and one of them was particularly obsessed with this protein folding problem, and still works on protein structure today in Cambridge as an academic, and always sort of thought, first of all, that it would be tractable one day, but also that it would be enormously important if one could solve this problem. And I've always loved this problem. I've always thought it would, I sort of filed it away in the back recesses of my mind as one day to come back to as we progress with AI, because I thought it would be very suitable for AI for a number of reasons. So the protein folding problem is quite simple to explain. Proteins, for those who don't know, obviously the workhorses of biology, they're essential to all life. Everything in your body is pretty much supported by proteins, and of course we'd like to know their function. And their function is partially specified by their 3D structure. So if you imagine the protein is specified by its amino acid sequence, which you can loosely think of as its genetic sequence, and then in nature it folds up into this 3D structure, and that's what kind of governs its function. Now, determining the structure of these proteins often takes many, many years. If you're going to do this experimentally, a lot of painstaking work. Perhaps many of you in the audience work on these things. And you know, the rule of thumb that again biologist friends have always told me is it can take a whole PhD, you know, 4 or 5 years to maybe even crystallize and figure out one protein structure. So it's really a lot of work. And Christian Amundsen, very famously in his 1972 lecture, for his Nobel lecture, speculated that the 3D structure of a protein should be fully determinable by the amino acid sequence. In other words, we should be able to predict this 3D structure immediately based just solely on its sequence. Now, of course, that then triggered literally a 50-year kind of grand challenge in biology, and people have been trying to make progress on this ever since, and it's obviously a whole field in itself. So why is this such a hard problem to solve the structure prediction problem, the protein folding problem? Can it be solved computationally? And why is this such a hard problem? Well, again, according to a contemporary of Vinson, Leventhal paradox, you know, he sort of back of envelope calculated that maybe there's roughly 10 to the 300 possible conformations that an average protein can take. And yet, obviously, the paradox is that in nature, obviously spontaneously, you know, within milliseconds in many cases. So how is this possible? How does physics solve this then? You know, is the big question. And the other reason we picked this problem is that there's a fantastic, really well-run competition called CASP that runs every 2 years, and it's been running for nearly 30 years now, and it's considered to be the gold standard benchmark in protein folding to test the best computational systems. And it's a blind test, so experimentalists submit their structures just prior to publishing for the competition, and computationally you have to submit your prediction, and then later on they reveal the ground truth structure, experimental structure, and then you compare the ground truth against your prediction. And usually for every cycle of the competition they have around 100 proteins that they collected like that they sort of withhold publication of. So AlphaFold 2, as many of you know now, did achieve atomic accuracy. So this is accuracy of the computational prediction to within the width of an atom, which is what we were told was the tolerance for it to be useful for real-world biology and chemistry. And we achieved this accuracy at CASP14, the 14th edition of CASP in November 2020. And if you look at the progress of CASP and the winning team, this is the score of the winning team in each of the editions back the prior 10 years to we entered, so from 2006 to 2016, there'd been almost no progress on the hardest category, so-called free modeling category, where there are no prior templates for these proteins. And you know, this score on the y-axis is you can think of it as roughly, it's called GDT. You can think of it roughly as the percentage of residues you've got accurately positioned to within a tolerance, a very tight tolerance. And so they were stuck around 40 pretty much, which is not useful in any way for experimentalists. It's far too large in errors. And in 2018, we entered for the first time. We started this work in 2016. The whole project is probably the most complex project we've ever worked on, and we started it literally pretty much the day after we came back from Seoul, from Korea, from the AlphaGo match. This was the next big project we took on. And AlphaFold 1, we entered into CAS13, and for the first time ever, we sort of entered a system that had cutting-edge machine learning at the core of the system for the first time. And it improved accuracy immediately from the previous sort of winning scores by around 50%, as you can see here. And then we totally re-architected AlphaFold 2 with a whole bunch of new innovations and taking the learnings from AlphaFold 1, and then that finally reached a